Hello everyone, today we'll discuss contest 13. I'm pre-recording this video because I will be out next week. So I recorded before contest end. I don't know the final results, but already Enslaved solved all the problems. And based on the timings of his solution, I would say that difficulty is much better than the previous one. So he solved all the problems in less than 2 hours. And the difficulty grows gradually, like I expect it to be. So let's discuss the polar problems. So in problem A, what do we have? We have n doctors. We need to visit them one by one, and each doctor will have this schedule. Maybe one again, you need to read all this problem statement, understand what's going on, but then you read the constraints. And this is one of the most important part, actually, usually the most important part of the problem statement is constraints. So you can see the constraint up to 1000. So if you look at numbers you have, you don't need to solve the problem for all possible inputs. Yes, you solve problem for inputs that satisfy given constraints. So you need to find the solution that works in like 2 seconds when all numbers are up to 1000. It kind of suggests you that solution which works in like n squared time complexity will do. Yeah. So n cube will possibly not pass, n squared will definitely pass. Actually, this problem can be solved faster. This problem can be solved in linear time. If you're good in number theory algorithms, I guess not in algorithms, just good in number theory, it's not that hard. But you're not expected to solve the problem in linear time complexity. N square will do just fine. So let's see. So how you solve it in n square time complexity? No, n square like n multiplied by d, let's say. So we have n doctors. We can visit them one by one. For each doctor, we can just simply wait for the day when this doctor will be available. And because each doctor works at least every 1000 days, so we will wait at most 1000 days before this doctor becomes available. So we can just iterate over all days and just one by one, and just check which day will do. And that's it. So we have 1000 doctors, wait 1000 days. So in at most million days, we will be fine. So let's look at my solution. So I solve problems like this. So I read the data like usual. Here t is my current day. So I iterate over all doctors one by one. For each doctor, I skip one day first, because I need to wait one day before I visit the previous doctor. And then I wait just until the doctor becomes available. So doctor is unavailable if my time is less than s, or if this difference is not divisible by d. Yeah? So I just check if doctor is not available, I skip this day. And do it until doctor becomes available. Yeah? I wait in this while at most 1000 iterations, so total number of iterations will be like million. So that's it. So this is the solution for problem A. Problem B is only implementation problem. So you just need to, again, read the problem statement and what's going on, and then program it. Very programming problem, nothing actually to talk about. So you just read this string of 12 characters, try to split them into rectangle A by B. So you check all pairs A and B with product equal to 12. Not that many of them here. So you just checked all of them and try to check if you arrange these characters into like this number of rows of this number of columns, you will have at least one column full of crosses. Pure implementation, no mathematical thinking needed actually, so just implement what's needed in this problem statement. Again, let's look at my solution. Well, first of all, let's look at my template for this problem. So I have special template for multi-test. So when you have problem with multiple test cases in the same input, I usually do it like this. I have this just main function which reads number of tests and then call special function, and I put this function solve inside this structure to make sure that all the variables are nullified when I call each time. So I can make some global variable here, just let's say 0, yeah, and it will be equal 0 on every call of this solve function. So just so what I'm doing here now, just do what's needed in this problem statement. So I read string, look for height of my rectangle, check if it's not divisible, then skip, then calculate the width. Now I have pair of height and width, and I check if I have a column of crosses. So I look for all columns, check if this column contains at least one then it's bad. So if I have good column, then the result is true. Now if this pair is correct, I put this width to my answer, and then in the end, okay, I put width, and here I put that. Okay, it's strange. Yeah, I should have put h here. Yeah, instead. So I iterate over everything I put it to my answer, and just output the result. Again, simple implementation problem. Nothing actually to talk about. So just again, you're programmers, so you just need to. It's some part of your job. So you read the problem statement and carefully you implement what you need to be implemented. I think that's it. So that's problem B. Pretty much the same for problem C. Problem C is only implementation heavy, nothing actually, no mathematical thinking required in this problem. You probably need to find a way to implement it carefully with proper data structures. What I'm doing here, I use map just. For every word, I remember its translation to the second language. And if the second translation is worse than my word, I will just skip it. So for every word, I just remember what should be put in the output if I see this word. Yeah? So if the same word in the second language is better, I will just remember word from the second word. If my word is better, I will just keep it. So let's look at my solution. So I'm reading all the pairs of words, yeah, and put them in this map. So this map contains a better translation for my word. Yeah. Again, I check if the word from the second language is shorter, strictly shorter. Yeah? You need to be careful. So if they have the same length, you pick the word from the first language. Yes. So if the second word is strictly shorter, then I put it as a translation of A. If not, I just keep translation of A as A. And now I just read all the words from my lecture, yeah, and output the corresponding translations. Yeah. Again, nothing really fancy, just implementation problem. Again, like it's quite common for the first few problems of the contest to be more like implementation problems. So you just need to spend some time and carefully implement what's going on, and try to train your problem reading skills. So you need to read this problem as fast as you can, understand what's going on, and then implement it as fast as you can, so you don't spend much time solving these problems. Okay, let's go to problem D. Problem D, on the other hand, has pretty much no programming, but requires some thinking. I wouldn't call it mathematical thinking, but you need some research what's going on in this problem. Well, let's see. So what we have like array of n apartments. Well, some of them are occupied, some of them are not occupied. So we have two problems actually here. We need to find the minimal possible and maximal possible number. Yeah. Let's talk about maximum first. It's actually surprisingly easier. So what can you say about maximal number of good apartments? So apartment is good if it has some occupied neighbor. So how many good apartments can we make? So if we put one neighbor, so if k equals 1, so we can put them here, for example. Then these two apartments are good, yeah, and so on. So every time we put one new occupant, so both neighbors became good apartments. So if we have k people here, so their neighbors are good apartments. So we have something like 2k good apartments, yeah, like 2k. Now, what will happen if you continue doing this? So if you continue doing this, at some point you will reach the end of your array, and then something different will happen. So So here you will have only one good apartment, and so on. Now each next occupied apartment will reduce the number of good apartments, because all apartments are good now. Yeah. So if you put your occupant anywhere, you decrease the number of good apartments. So in this case, so let's see this case. In this case, when we reach the end and now fill in the good apartments, the number of good apartments will be something like n minus k. Yeah, because all apartments are good except which are already occupied. Yeah, and so the answer goes something like this. So it first goes like 2k, so it grows like 2k. Then at some point it starts decreasing like n minus k. Yeah, so it's like 2k here, n minus k here. Now when you see that answer is something like this, you need to carefully look what's happening here. In some problems, you may have some corner cases in this region, yeah, because when you reach this point, move from one tendency to another tendency, you need to some strange things may happen. So you carefully think what will happen in this region, and if you see that nothing actually will happen in this region, so when you reach the end, so if you have enough space, you will put another occupant and have two good apartments. If not, then you put occupants, and now all apartments are good, so you have n minus k. So for every values of n and k, at least one of these formula will work. And actually the answer is just minimum of these two values. Yeah. So you have this line, and the minimum of these two lines will all be the answer. So minimum of these two is actually your answer for the second question. For the first question, it's a little bit more tricky, surprisingly, because let's see. It looks like, so we want to find minimal number of good apartments. It looks like this number is kind of always 1, yeah, because we can put all the occupants here, so this is the only good apartment. It looks like the answer is 1, and when you see something like this, you think, why it's always 1? Can it be not 1? No, we can always make it at most 1, but can it be less than 1? And it actually turns out it's possible to have less than 1. We have 0 good apartments. It happens actually in two cases. One case when all apartments are occupied, so when n equals k, and another case when nothing is occupied. So when nothing is occupied, you also have 0 good apartments. So if k is 0. So if n equals k or k equals 0, the answer is 0 for the first question, and if not, the answer is 1. So that's it. So you have this solution for the first question, this solution for the second question. Well, here's my solution. No, it's quite trivial again. So again, like I told you, so for the first question, the answer is 0 if n equals k or k equals 0. And for the second question, just minimum of these two values. That's it. Kind of tricky problem. I actually missed one of the cases, this case, I believe. I missed this case when I first solved this problem. So you need to be careful. It's easy, but still tricky. It happens. So that's it. That's problem D. Problem E, football. So what we have in this problem, we have some tournament basically, and we know that each team won exactly k matches. And we just need to output any like match schedule which gives you this result. Again, it's not very hard problem, but it's tricky. Need to careful thinking and careful implementation. First of all, this number of matches should be equal to n multiplied by k, because we have n teams, each won exactly k matches. Yeah. So total number of matches in each match at least one team won. So we know that the total number of matches is the same number of times than some team won the match. So we have total number of matches is just n multiplied by k. And now we just need to carefully construct such a schedule. Many ways to solve the problem actually. Easiest way to do it like this. So we pick a team and pick other teams who who this team won in the match. And you can do it, like, for example, like this. You pick a team, and just if you arrange all the teams in a circle like this, let's put 6 teams. So you just so the first team will beat teams 2 and 3. The second team will beat teams 3 and 4, and so on. So every team beats next team in this cycle, like this. Yeah, and this. Yeah. So you just pick every team, pick next k teams, and beat all these teams. Looks easy. The only trick is then k is too large. It's just impossible to do, because every pair of teams should have at most one match. Yes. So every pair of team can play only once against each other. So when k is large, you cannot do it like this. So you have so for every team you have k teams you win, you have another k teams you lose. So if total number of these teams is more than n-1, then it's just impossible. Yeah? So it's impossible when 2k is actually greater than n-1. What you may think about, so is it really impossible? So when you see that your solution doesn't work for some cases, you just think, is it really impossible? Why is it impossible? Maybe I'm missing something. And the proof is actually easy. You can just, sometimes you can just believe it's impossible. Sometimes you can prove it's usually better to have at least something in it, at least why it's impossible. And the simple reason actually is to count total number of games. So total number of games is n by n-1 divided by 2. Yeah. And total number of games we need is n multiplied by k. If n multiplied by k should be less or equal than this number, yeah, and it immediately gives you the same thing, yes. So for this problem to have a solution, we need k. So you can remove one n from both sides, yeah. So remove n from here, remove n from here. So k should be not greater than n-1 divided by 2. Let's move this 2 to the right. Yeah. So 2k should be not greater than n-1. If 2k is greater than n-1, it's impossible, because you have too many games here. So that's it. So let's look at my solution. Like I said, the programming part is kind of easy. So you check for impossible. I usually check for impossible before I do anything, because something strange may happen. So if you have some impossible case and you try to construct it, then in the middle you may have some unexpected situations. So I just, before I do anything, I check if it is impossible, then I return impossible. And then if I'm sure the solution exists, then I try to build it. Yeah. Sometimes it's hard to build things which doesn't exist. Yeah. So I check if it exists. If it does exist, then here I build it. Yeah. No, I build it like I told you. So I take every team and take next k teams. So my index will be I plus 1, and this index will be I plus j plus 1 modulo n. So it's my number shifted to j plus 1 positions modulo n, and then plus 1. Yeah. Because I'm moving from 0 notation to 1 notation. That's it. Nice problem. Not actually that hard, but again, have some tricky cases, need some clever programming. Let's move to problem F. Problem F. So problem F introduces some, maybe not a familiar for you term, it's because minimal by inclusion segment. Minimal by inclusion basically means you cannot decrease it. Yeah. So you have some set, you cannot throw any element from this set. So all elements of the set are kind of important. In this set, it's not set, it's segment. So it is a segment which you can shorter. Yeah? So if your segment is good, but if you decrease it, any border of the segment, you will have a bad segment. So it's called minimal by inclusion. So all segments included inside this segment are bad segments, but this segment is good segment. And in our case, good segment is the segment which contains exactly k distinct elements. Multiple ways to solve this problem again. First of all, you can find the segment of minimal length using two pointers method. I believe I have a lecture about this, but not for today. So even harder problem of finding just segment of minimal length. Segment of minimal length is always minimal by inclusion, if you can prove it easily. Even this harder problem is solvable, but here it's much easier. So there are many ways to find minimal by inclusion segment. Usually you do it like this. You get some good segment and then throw away elements until you have a bad segment. Yeah? And then you just stop before. So you have some good segment and you try to remove elements from its ends until you have a bad segment. If you cannot remove elements from both ends of the segment, then you have minimal by inclusion segment. I actually used even easier approach, I think so. I do it like this. Let me show you. So I do it like this. So I have my array. So first of all, I find the shortest prefix which has k elements. So I add elements from left to right until I have the prefix which has exactly k different elements. Yeah? It may be not minimal by inclusion, because I cannot move this border, but I probably can move this border. Okay? So again, I greedily add elements from left to right until I have k elements in my set. Now, then what you can do, you can remove elements from the left part, but it's kind of tricky. So it's possible. So you can remove elements and still check how many different elements you have. You can maintain like map of counters. So for each element you count how many elements you have, and then you can carefully track how many different elements you have in your set. It's possible, but it can be solved easier. So what I'm doing instead, so again, when I go from left to right, I kind of fix this right border. So I know my right border is here. So right border is unmovable, but left border is movable. Instead of moving left border, I just start from this right border here and just go from right to left and add this element. Instead of removing element, I will just add elements until I have the first time when I have k elements. Yeah. So I first fix the right border, and then go from right to left, fix the left border. One of the ways to solve it. Again, many ways to solve this problem. Just find. I believe you need to find your own way to solve this problem. So let's look at my code. I do it like this. So I maintain simple set of integers. Set is the perfect data structure. Luckily in C++, you have sets. You can do it like this. So here I greedily add elements from left to right until I have size of the set equal to k. Then I check if it never happened. Then I just output impossible. If it happened, I fix the right border. Then start from the right border, I go to the left. And again, do all the same thing, add all elements until I have set of size k. Then I stop. Then I fix the left border, fix the right border, I'm done. Here I just change from 0 notation to 1 notation, and right pointer is exclusive. Like I usually keep all the segments in such a way that left border inclusive, right border exclusive. Yeah. So left border is inclusive, so I need to make +1. Right border exclusive. Yeah. So the rightmost element is like r minus 1, but when I move from 0 notation to 1 notation, we make +1. So this is one L +1, but here is just r. That's it. That's problem F. Problem G, I believe the main difficulty of problem G is geometry problem. And everybody hates geometry problems. Okay, not everybody, but a lot of competitive programmers hate geometry problems because it usually involves some strange programming. But here, it's actually quite easy geometry problem. So if you're not very familiar with geometry, you still can do it. And it doesn't require actually a lot of geometrical thinking. Yeah, it's mostly about some integer numbers. So how to solve this problem? No, first of all, when you have a geometry problem, you need to draw a picture. Never solve geometry problem without a picture. You need to draw at least one picture explaining what's going on. So let's draw a picture. So what we need to build? We need to build some triangle, boom, like this. Here's the right angle, with legs of size A and B. Now, we need to find coordinates of 3 points. It's 6 numbers. That's too much. So let's try to simplify it. So what we can simplify? First of all, let's put this corner in the in point 0, 0. In like so we can move our triangle, yeah, along our plane. So let's move it in such a way that this point goes to the point 0, 0. Okay, now we have only 2 points to find, yeah? So we already know coordinates of one of the corners. So we just need to find these 2 points. Now, let's orient our triangle in such a way that this point is in the positive quadrant, yeah? We can always do it, yeah? So all coordinates are not zeros now. If we have 0 coordinate when we have side parallel to axis, so all coordinates are not non-zeros. So let's like shift and rotate our triangle in such a way that this point have positive coordinates. So it has some positive coordinates x and y. Well, let's say x a and x a. So we have coordinates of both points. Yeah. Now let's see. So constraints are so we have constraint up to 1000. Yeah. So we can brute force something. Actually, we can brute force both coordinates. Yeah. So we have. So if we brute force both these coordinates x and y are not greater than 1000. So we can actually brute force both of them. Yeah. And find all pairs that gives us this leg of size a. You can check it by Pythagorean theorem. Yeah. So you can say that xa square plus ya square equals to a square. So you can brute force over all pairs of coordinates x and y and check if they satisfy this equation. If they satisfy this equation, then we have a segment of size a. Actually, it's enough to brute force only one coordinate. So if we know coordinate x, we know a, we can calculate coordinate y. It will require some square roots, but still it's doable. Yeah. So it's actually even solvable if a and b are up to, let's say, million. So it will still be the same. But we don't need it actually. So if you come up with a solution which works in like 1000 square, it will still work. Now, so we know coordinate of 1 point. Now we need to find coordinate of this point. Easy way to do it is actually to see that now we need to calculate. No, here you need to think like this. If I fix this point, then I can actually fix all my triangle. Yeah. So I know my triangle. So it's like this. Yeah. It's the same triangle. We can just rotate it and shift it. So if I fix one of the legs of my triangle, yeah, then I fix the position of my triangle. So it should be possible to calculate this point. The question is only how to calculate this point. And then you just carefully draw the pictures and understand how you calculate this point. Now, the easy way, I believe, is to see that these two triangles are similar. So this triangle and this triangle, because these angles are the same. Yeah. So coordinates of this point I actually can be calculated like this. So x coordinate of point B is the same. So x coordinate. So this part is the same as this part of this triangle. Yeah. So it's y coordinate of point A. Yeah. But multiplied by B divided by A. Like this. Now the only problem is we need to check if this point is integer. So there are multiple ways to do it. We can just check. We can just check. So we need to check that y multiplied by a multiplied by b is actually divisible by a. Or you can divide and then check, like I did in my solution. So you can just divide, find some point, then check that the length of this segment is equal to b. If it's not divisible, it will be less than b. It will be closer to here, it will be not to b. So up to you. So again, you just, again, what I did, I just fix one coordinate, this xa, then calculated coordinate ya, then calculate coordinate xb, and in the same way calculate coordinate yb. It will be again xa by b divided by a. Check that both of them are integers, or check if this side is equal to b. Finally, again, so we know this segment is not parallel to axis, this not parallel to axis. We just check this this segment is not parallel to axis. And I believe we check that yb is not equal to ya. Yes. I actually think it cannot be equal, right? Yeah, I think it's too much actually. I did it in my solution, but I believe it's impossible to build right angle triangle. Yeah, because this length will be some square roots of 2. Yeah, this length cannot be integer. It will always be square root of 2 multiplied by integer, so it's never be integer. So okay, so it's redundant, but again I did it in my solution. So let's look at my code. So I did exactly what I told you. So yeah, so I iterate over coordinate of point A. I call it ax. It doesn't matter. So it's coordinate of point A. Calculate coordinate of point or y coordinate of point A using this formula. Here I'm using floating point numbers. You need to be careful doing this because numbers are small. It's okay. Yeah. In some other problems you may have troubles here. No, see, since numbers are small, and I know that this number must be square of integer number. If it's not, then this check will just not work. So I calculate some coordinate of point A, and then check if it works. Again, if this number is not a perfect square, then I will have some wrong value here, but then this check will not work. Then I calculate coordinate of point B, check if this length of this segment is equal to B. Again, instead of this, you can check that just this division actually divides. Yes, so both these numbers are divisible by A. Okay, this check is redundant. Okay, and here I just output the result. That's it. Not very hard problem, but again, the main difficulty is geometry problem. Yeah. You need some experience in geometry, I believe. So if you didn't solve any geometry problems before, that's a good problem to start. Okay, let's go to the last problem. Okay, the last problem. So we have two tabs. One can give us amounts from 0 to x1, another from 0 to x2, some temperatures, and when we pick some number here, some number here, we calculate the final temperature like this. And we need this value to be greater or equal than T0, but as close to T0 as possible. What does it mean? So we pick only values greater or equal than T0, but from all these values we pick the minimal one. Yeah? So we need to find the minimal possible temperature less or greater or equal than T0. Okay, the tricky part is actually, this is another tricky part. So if there are multiple ways, you need to find the quickest as possible. It just means we need to find a solution with a maximal amount of water as possible. So if there are multiple ways to have the same temperature, we need to pick one with the maximal possible amount of water. It actually turns out to be tricky. I made some mistakes here, but let's talk about this. So first of all, again, look at the constraints. You read the problem, look at the constraints. Constraints are up to 10 power 6. 10 power 6 kind of suggests that you can iterate for all values. Yeah. So at least one of these values, I have two. So y1 and y2. So at least one of these values I can just brute force. Yeah. So imagine I know value of y1. Now what? Now we need to find value of y2. How we do it? We look at this formula. So let's carefully just write down what this formula means. So what do we have? We have our temperature, it's equal to T y y1 plus T2 y2 divided by y1 plus y2. And we need this temperature to be at least T0. So let's move this to the right. So we have Ty. It's basic algebra actually. Very simple. Greater or equal than T0 multiplied by y1 plus T0 multiplied by y2. And again, what we're looking for? We're looking for value of y2. So we know all the values except y2. So let's put everything connected to y2 to the left. So we have y2 multiplied by T2. We move this to the left, yeah. So it minus T0 greater or equal than T0. Okay, y1. Let's move y1. y1 multiplied by T0 minus T1. And now let's divide by, so now every time you divide, you check that number you divide is not 0, and if it is positive, yeah, you cannot divide in equations by non-positive numbers. So now here you carefully check that T0, T2 minus T0 here, it's non-negative, so it may be 0. So I will add the question mark. So this part may be 0. If this part is 0, this is some strange case. So let's think about it later. Yeah. So if it's not 0, then it's positive. Then I can divide. Then y2 must be greater or equal than y1 multiplied by T0 minus T1 divided by T2 minus T0. So all these values of y2 will give me this string. Yeah. So if I pick any value y2, then temperature will be okay. Now, from all good temperature, I need to pick the minimal one. Yeah. So y2 is amount of hot water I put. Yeah. So if you increase amount of hot water, the temperature will grow. So you basically need to find minimal value y2 required. Yeah. So when you pick value y2, you pick the minimal value required, which satisfies this equation. Yeah. So basically y2 will equal to, say min, will be equal to this thing flow. Yeah. That's it. It turns out there is another tricky case in this problem, but let's talk about it later. Now let's talk about this equals 0. So what happens if this part equals 0? If this part equals 0, it means that T2 equals to T0. Yeah. So hot water is just the temperature we need. Yeah. So if we just add hot water, we will have exactly temperature we can't go above this temperature. Yeah. So basically what we need to do is to okay, so let's put it here. So if T2 equals to T0, then we need to have y2 equals to x2. So we put all possible water of this temperature. What happens to the cold water? Can we add any cold water? It turns out we actually can if this temperature of cold water is actually the same. So if the cold water is the same, we also add everything possible from the cold water. Okay, so this is special case. Again, like I always do, I will track all special cases before and then do all the rest. Another special case, surprisingly for me, is when y1 equals 0. So if I don't put any cold water. And so what will happen? So what's the difference? The difference is that here. So I told you that all values y2 are good, but since we're looking for the minimal value of temperature, we pick the minimal value of hot water. But if we don't put any cold water, then if we increase amount of hot water, the temperature doesn't change. Yeah. So if the temperature doesn't change, it happens only if y is equal 0. Then we have y2 equals to x2. Okay, that's tricky case. I missed it when I first solved the problem again. So it's happened. So how you track cases like this? No, you carefully think. So you get wrong answer test 6. You think, okay, what have I missed? And just carefully look for. So again, the only tricky part of this problem, I believe, that if again this property that if there are multiple ways, then you fast quick as possible. So you need to output the maximal amount of water you can put with the same temperature. So this is like the tricky part of the problem. So you look for the bugs in this area. So if I found some solution, but is not a solution with higher volume, can I use this solution instead? And just look in this direction, and if you're lucky enough, you will find this tricky case. So let's look at my code. I remember another problem here is that you need to find the minimal temperature closest to T0, and I do it by comparing fractions. Yeah. So I have some rational numbers. I put them in these fractions like P and Q here. And I compare them in integers, because if you compare them doubles, you may have some troubles. Yeah. So when you have doubles, they may be very close. So you will have some precision problems. You don't want to do it. So so again, all numbers I need to compare are of this form. Yeah. So all these numbers are integers. So this fraction is some rational number. So I compare rational numbers by doing like something like this. So okay, let's read the whole solution. So here I track all the special cases. So when T1 equals T0, so when T2 equals T0, I check if T1 is also equal to 0. I output this. If not, I'll put this. So here I just solve all the cases when T2 equals to 0, because here I'm dividing by T2 value. I don't want it to be 0 here. Yeah. So I just check before. If it is 0, then I do something else. Now here I track all possible values of y1. Yeah. Calculate minimal possible value of y2. If it is greater than x2, then it's impossible. Yeah. So this value of y1 doesn't work. Here I track this special case when y1 equals 0, then you need to put y equals x2. This nice touch of this problem. I love problems like this. Here I just calculate final temperature as a fraction p divided by q. Yeah. And then I compare this fraction with my fraction. So I have some result. Initially it's -1, so here. And I check if it is -1, so if it is not found yet, or if my solution is better or equal. If it's equal, then okay, for highest amount of water, I will just rewrite it. Yeah. So if my solution is not worse than existing solution, then I rewrite it. That's it. So in the end, just output the result. Again, not very tricky problems. It has some interesting points. Overall, quite solvable problems. Okay. So again, what you need to care about in problems like this, first of all, look at the constraints. In some another problem, you might have different constraints. So here, since the constraints are up to million, let's think about some brute forcing of one of the parameters. So you have two parameters. You think, okay, I can brute force one of them. And then you think what you do with the second parameter. Now you involve some maths. So you write all the formulas and try to calculate the second parameter. And you have some another tricks like comparing fractions and dealing with some corner cases. Nice problem, actually, like it a lot. So that's it. That's what kind of quick, because I don't have audience and I don't program online. So I just read all the pre-recorded solutions. So thank you for watching. Again, see you next week.